In this section, we'll look at a couple practical examples of PDFs, and specifically we'll just look at a uniform probability density function and then extend that into piecewise probability density functions. So starting out, let's revert back to our discrete version, the probability mass function for a uniform probability mass function, and that's what we've got right here. But this probability mass function, we said, was ultimately able to be defined by an equation if it's uniform. We said that if we have all of our values constrained within some area A and B, or two values A and B, that the probability of each of those unique values, each of those discrete values, was equal to this equation, and it's 1 over B minus A plus 1. We said that it's the difference between these plus 1, assuming that every single integer value here has a probability mass associated with it. The probability mass for that region for every single one of those outcomes would be equal to this equation. Now, we can do a similar thing for continuous random variables, and specifically for a continuous uniform probability density function. And that would look something like this. Now, this is actually a really easy probability density function to describe, but let's remember a couple of rules first. We said that the probability density at any specific value must be greater than or equal to 0, and you can see that for this to be uniform, that's true. But we also said, more importantly, that the probability density for all values, so from minus infinity to infinity, the probability densities had to sum to 1. Again, that integral from minus infinity to infinity of the probability density function must be equal to 1. For that to be true, we already know our width here, and our width is ultimately just B minus A. And so whatever we do, if this is the region, this B minus A region is what we're limited to for our probability density function, then we can actually just write that the probability density function, or the probability all the way across that PDF, is just equal to 1 over B minus A. So when you multiply this together, you end up with the width, B minus A, multiplied by a height, 1 over B minus A. The B minus A's cancel out, and you're left with a total density of 1, or a total probability of 1. Now, this can be extended to probability density functions that have discontinuities. So let's look at an example here where we have really 3 different uniform regions, and we can break this up into our 3 regions. And again, the same rule applies, which is that from minus infinity, way over here, to infinity, if we were to sum this entire area, it would have to equal 1. So you can still have discontinuities. You would treat this as 3 separate integrals. So you'd have an integral from A to B plus the integral from B to C plus the integral from C to D. But once you get all of those integrals summed up, they must equal 1. Now, depending on the width and the values associated with those, then the probability will vary. The probability density, the value up here, will vary for each of those blocks. But this general statement here, that the sum of all the integrals must equal 1, always has to hold based on the definition of a probability density function.